Hello, I am Chris Selkvist, and I'm presenting the safe, fast sharing of Memcached as a protected library. Memcached is a very important data caching service used by a variety of online services such as Facebook and Twitter to cache frequently used data that's normally stored on disk. Applications that wish to store and retrieve data to and from Memcached can do so by passing a request to the Memcached instance over a socket. There can exist many different Memcached instances distributed across the network, each storing a fraction of the total working set. Sockets are necessary for communication across nodes, but are wasteful when communicating on node for reasons I'll discuss. Sockets are often used to implement message passing interfaces, like the one Memcached uses. End users request over the socket that Memcached instances perform various queries on their behalf, and then they receive a packet back containing the results of that query, like what is shown in the diagram. Sockets incur quite a large overhead through repeated kernel intervention and complex network protocols that don't appear necessary for accessing data that's already in memory. So how do we get rid of this overhead? Well, we could put all the data in shared memory and allow users to perform the queries themselves. On the plus side, there's a potential for a 2 to 3x speedup, but on the other hand, the reason this isn't already done is because it isn't particularly safe or easy. A user with Memcached structures in shared memory could, for instance, accidentally do a stray write and ruin the coherence of Memcached for everybody else. Luckily, we have Hodor, a mechanism for process isolation that can give us the speed we want from direct access to shared memory and the security that we had under a message passing protocol. Not only can we get the speed of shared memory and security of message passing, but we can do so with very little additional code. Hodor works by providing a mechanism that allows us to switch between a library and a non-library mode using Intel's hardware feature called Protection Keys for User Space, or PKU. We create a separate heap for our library and mark it as belonging to this library mode, so that any future accesses outside the library mode will result in a segfault. The only way to switch between modes is via functions called trampolines that the developer has marked ahead of time. Hodor guarantees that these are the only functions that will be able to do the switch between modes. As well, Hodor guarantees that if a process were to die for some reason outside the library code, any calls in process will continue to completion so that structures may remain intact. All of this will allow the user the ability to access Memcached internal structures directly without incurring the overhead of sockets, but restricting this access to a preordained list of developer-defined functions. An additional benefit of moving away from message passing interfaces and towards Hodor is that writing interfaces this way is much easier both in terms of complexity and code size. Memcached had a very customizable interface that made for a complicated code base that was hard to debug. Because the operations using Hodor are simply function calls, debugging became much easier. So then how do we use Hodor to get all the benefits I've mentioned? First of all, there's integrating Hodor itself. And then we have to make sure that all the resources necessary to make a Memcached query are accessible over shared memory. And since we can't guarantee that these resources will be mapped to the same exact point in memory every time, Memcached has become position independent. Finally, we have to make Memcached absolutely bulletproof to misbehaving users. This sounds hard, but actually turns out to be relatively hassle-free. One difficulty with shared memory is that it's not entirely easy to do memory allocation in a shared segment across multiple users of that shared memory. Luckily, we have Ralloc, a memory allocator that gives us all the properties we need to make memory allocation in shared libraries simple. First, it provides utilities such as smart pointers that allow us to make Memcached position independent without rewriting our whole code base. Second, it places all allocations into a file, allowing us to easily map it into a user address space without the need for classical shared memory utilities. And third, this file is resistant to being opened by arbitrary users because Hodor initialization routines, wherein all resources are mapped in, are performed as root. This clear delineation between user and library is necessary not only for shared access, but also because for Hodor to function efficiently, we need to know where the entirety of library data will live ahead of time. So now that we can make Memcached available over shared memory, how do we do it safely with Hodor? The vast majority of the codebase can remain exactly the same, except that the developer needs to mark which functions an end user should be able to access using the directives you can see above. By simply labeling the function with a function annotation and exporting the function name with number of arguments, which you can see after the function body, Hodor automatically instruments all functions at runtime with the switches from non-library to library mode. As well as annotating trampoline functions, the developer needs to write initialization functions. In this function, we map in the Memcached file into memory using ralloc in the first bolded line of code, and we use pku syscalls to mark all the pages as belonging to the library in the second bolded line. At the very bottom, we also export the function as being a Hodor initialization function, which notifies the Hodor runtime to call this function before main is entered. Notice here that we set the value of the isRestart flag with the result of the ralloc initialization call. This tells us whether or not we are starting from a fresh, empty file, or we are opening a file that presently contains the Memcached instance. Using the isRestart flag, we can initialize the rest of the service. Here is an initialization function that we called from within the one from the previous slide. Differently from before, this one is used to retrieve our global pointers from the ralloc file. Here, I've highlighted the lifecycle of the primary hash table pointer. If we are not restarting, we are running for the first time and need to allocate memory for our hash table within the file. We do so by calling rpmalloc and converting the raw pointer into a p pointer, ralloc smart pointer that is internally position independent. We then use rpsetRoot to set the root of primary ht to this value so that it can be retrieved and used if we are starting, which you can see on the final bolded line. Now that we have Memcached functioning in shared memory using Hodor, what else can go wrong? Well, now that we're directly receiving data from the user instead of reading it over a socket, user data may be nonsensical, so we need to validate it as we did before. If this data is stored in a structure delivered via pointer, a misbehaving user thread can now modify this data while we're inside the library, causing unforeseen behavior. To fix this, we need to copy all of our input into user-inaccessible buffers before use or even validation. But all this came with the assumption that the user gave us valid pointers to begin with. If a bad pointer is dereferenced while resources are held, Memcached will crash and leave the file in an incoherent state. Therefore, all data needs to be copied in and out while resources are not held. In the case of output, we copy output while resources are held to a protected buffer, and then copy from our buffer to the user buffer after resources have been released. If the user gave us a bad pointer, we will crash, but at least we'll crash without ruining the entire state of Memcached. Here are the results of these modifications. For both read and write heavy workloads, we see a 2 to 3x speed up of Memcached. Important to notice is the different shapes of the curves. Our modified Memcached peaks much earlier and begins to decline in throughput at around 8 to 10 threads. The important takeaway here is that the limiting factor is no longer the overhead of message passing, but is now the scalability of the data structures. This means that with better scaling structures and further optimization, the service could potentially see even higher performance than seen here. Latency was also hugely improved. For queries that do very little work, message passing is going to take up a larger portion of execution time, and therefore removing this overhead will result in a much larger speedup, which is what we see with delete and increment, for instance. And as for code reduction, we removed around a quarter of the code in the end. Ralloc is a slab-based allocator, and Memcached implements its own custom slab allocator. So to reduce redundancy, we removed it. However, most of the code reduction still comes from the removal of networking. We also added 600 lines for Hodor integration. Much of this code is quite simple and repetitive compared to the networking code, which is neither simple or repetitive. Not included in this total, of course, is the library libmemcached that Memcached provides to assist in communicating with Memcached instances. That's another 14,000 lines that the developer no longer needs to write. In conclusion, writing services as protected libraries gives us much higher throughput, reduces the size of the codebase, and doesn't compromise at all on safety or security. Memcached, of course, is a distributed service, and so this aspect was removed for our product because accesses are now only made over shared memory. However, a hybrid model where off-node queries are made over socket and on-node queries are made via Hodor is entirely possible. Future work includes applying these transformations to kernel functions and creating a persistent Memcached.